first thing we want to do today is look at the question of following kind. Look at this sequence. That's a sequence of 2 square equal to 4. If I take any two consecutive digits, just see what you get. One, 0. So now what you see is you get all possible pairs, all possible ordered pairs, 0, 0, 0, 1, 1, 0, 1, 1. What we want to do is do this in general. So the question is the following. So let me define this. A de Bruijin sequence is a binary sequence. A0, A1, A2, such that for all I, look at the sequence AI plus 1, etc. up to AI plus n minus 1. So look at this subsequence. The subsequence, the set of all subsequences exhausts all the 2 power n binary sequences of length n. So the example there is a de Bruijin sequence of length 2 square. If you take any pair, the possible pairs, the possible n tuples, n is equal to 2 in that case, possible pairs, possible ordered pairs, their number is 4, and all of them occur exactly once. So exactly once. This is to be read cyclically. This is to be read cyclically. What does that mean? So going from here, then I go back there that way. So these are written on a circle. They are actually written on a circle. So this is not linear. It's a cyclic arrangement. Okay? That was easy because the number was small. How would I handle something like even a moderately large thing like 2 cube? The next question would be 2 cube is equal to 8. Now I am looking for a sequence whose length is 8. Whose length is 8, A0, A1, A2 up to A7, such that every triple, order triple occurs exactly once as you go on. Let's see how this can be constructed. And then I'll write the theorem in general. So what I'm going to do is have ordered pairs, have pairs as vertices. Okay. Let me tell you what this is. This is a directed graph. It's a directed graph in which vertices are ordered pairs. So there are 4 vertices, all possible ordered pairs. I draw an edge between an ordered pair. There is an edge directed that way because delete the leftmost coordinate and adjoin, drop the left coordinate and make the new coordinate 1. What will happen is that 0 will go away and it will become 0, 1. Is this clear? It's like, what is this? I'm shelling off the left part and adjoining this on the right. So what I get is that vertex called 0, 1. If I leave that 0, the left 0 out, and adjoin that with 0 on the right, I still get the same vertex back again, therefore there is a loop there. Is that clear? So that's why I have a loop there. So that is the way that graph is drawn. That's the way that graph is drawn. This graph has the property that for every vertex, there are exactly 2 edges going out of that vertex. In fact, on every edge, there is a direction on every edge. On every edge, I have written number, either 0 or 1. So it tells you what using 1 from this vertex, you move to that vertex. Is that clear? If you drop that 0, adjoin 0 on the right, then it becomes 1, 0, and that's why you get to this vertex. Whereas if you drop that left 1 and adjoin that with right 1, then what you get is 0, 1, therefore you are back there. Is that clear? So that is the way this picture is drawn. So from this it is clear that at every vertex, there will be exactly 2 edges going out. There will be exactly 2 edges going out at every vertex and exactly 2 edges coming into that vertex. That's clear. Okay, I can quite easily see how this will look like if a vertex has the form something like alpha beta, where alpha beta are 0, 1, then you are going to remove this and replace. That's what is going to happen. That alpha will go away, where gamma takes 2 possible values, 0 or 1. Therefore, at each vertex the out degree is equal to 2. At every vertex the out degree is 2. In fact, there will be one edge which is labeled 0 and one edge which is labeled 1. In fact, the same thing is true about the in degree. If I start working backwards, that is what it comes to. Where does this come from? When we'll have to think backwards. So this is something like, what was it before? It was delta alpha and then you join beta there. Where delta can take 2 possible values. It could either be 0 or 1. And therefore, each vertex, the in degree is also equal to 2. So at every vertex, the in degree is 2, out degree is 2. This is a connected graph. And therefore, thanks to Euler's theorem, this has an Eulerian circuit. It has a directed Eulerian circuit. Now we are in a directed situation. So we have a directed Eulerian circuit for this graph. Let's start writing the directed Eulerian circuit. Let's begin with this vertex 0, 0. Let me use some different chalk. So first I begin at this vertex 0, 0. Whatever Euler circuit basically traverses all possible edges. How many edges are there for this graph? The number of edges at every vertex, the out degree is equal to 2, as I just said. There are 4 vertices. At each vertex there are 2 edges going out, therefore the total number of edges is 8. For every edge there is a label. So just record that label. So what I would do then is I begin at this vertex move that way, record 0. Then I go over here, record 1. Then from this, I go down that way, record 0. Then from this, I go that way, record 1. Then at this, I'm back at this vertex, go that way, record 1. At this vertex, finish the loop off. Therefore, you record 1. Then you go over to this vertex, record the label of that edge, which is 0. Then go over that way, record 0. Have I exhausted all the edges? Yes, I'm back to that vertex. I've written down as many as 8 binary digits. Let's check that these do actually cover all possibilities. Physically, 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, finally 0, 0, 1. My claim is I have exhausted all the possibilities, every triple in fact, these are all distinct triples. These are distinct triples, distinct binary triples, and these are all the distinct binary triples. 2 raised to 3, 2 raised to 3 equal to 8. Each binary triple has occurred exactly once as you go on. So these numbers, imagine as if they are written on a drum. Exactly, a cylindrical drum. You write them on a cylindrical drum so that you can read them that way. This model is actually used in practice when you write it on a drum. Why is it that it worked out quite all right? Why is it that nothing got repeated? The answer to that is roughly as follows. As I write the numbers, just see what has happened here. First I wrote 0, that's what I did, going over that edge. Then I went over that edge, 0, 1. This already is a vertex. The first 2 digits, when I write, this is a vertex in fact. The next digit is 1, is 0. So 0, 1, one can call that kind of thing as a flag. So vertex along with a direction. The claim is you cannot really have a situation where the vertex will also be repeated and the direction will also be repeated. In that case, it must be the same, absolutely the same numbers and the same direction. And that is the proof that Bruijin sequences exist. So that's the theorem I want to write down. For every n, there exists a Bruijin sequence and essentially the proof is we'll have to mimic that. That is what we'll have to do. So in terms of write up, it will be somewhat messy, but it's clear what is happening. Draw proof. A directed graph with vertex set that consists of n minus 1 tuples, n minus 1 binary tuples we draw thus each vi is equal to 0 or 1. We draw an edge with label V to W, where, okay, how would this, W is V2, V3, etc. up to Vn minus 1, W1. The leftmost digit is dropped and the rightmost digit is the new digit that is added. Is that clear? That is the way this is happening. It's a very peculiar construction. It's a very peculiar construction. Leftmost digit is left out. You drop it, replace that by a digit on the right. So it's a shift involved there. Okay, V2 was the second digit initially, but now it becomes the first digit, etc. And a new last digit gets added. It then follows that each vertex has out degree 2 and in degree also 2. In fact, at each V there is exactly one edge going out with label 0 and one with label 1. Thus, we have 2 power n minus 1 multiplied by 2 equal to 2 power n edges in all, and G is connected. So G has a directed Eulerian circuit. That covers all the 2 power n edges exactly once. We record the labels of edges as we traverse this circuit. Giving us a sequence, a binary sequence of length 2 power n. We claim that this sequence is a de Bruijn sequence. So the explanation is like this: if I is strictly less than j, then ai plus 1, ai plus n minus 1 equal to bj plus 1, bj plus n minus 1 implies see, the situation is just like this. This is the vertex ai plus 1 plus n minus 2. That means this vertex is equal to this vertex, and that label is also equal to that label. Okay, so if this is 0, then this also would be 0. If whatever this word, that means they are equal actually. That means you are at the same position. So that's sort of the proof that this is a de Bruijn sequence. So it's a fairly nice construction, quite a nice construction. Yeah, is this clear? What is not clear then? This will become a vertex. That's exactly what I'm. Okay.
The 2 points.
Sorry?
Okay.
This is a vertex. It will, as you go on adding the edges, actually what you see is a vertex. First I have the input 0, then I have input 1, 0, 1, where I have reached actually is that vertex. The next thing if I add, it is, what did I say, 0. So it is like 0, 1 and then followed by 0 that way. How can that be equal to some other vertex and followed by? That cannot be unless that vertex is equal to that vertex and the input is also same. Therefore they are exactly one and the same thing. Okay, which is contradiction because you are saying that this is an Eulerian circuit. So everything is happening exactly once. You are going around exactly once. As an exercise, find de Bruijn circuit in the situation of 2 raised to 4. So find a de Bruijn circuit or find a de Bruijn sequence of length 16. So what is it that you would be doing? What you would be doing then is you would take as vertices to order triples, binary triples. So there would be as many as 8 vertices. Draw the graph. Actually construct an Eulerian circuit on that graph, which would not be very difficult. And then get the de Bruijn sequence. So you get a binary sequence of length 16 in which every 4 tuple consecutive digits, they will exhaust all the 16 possibilities. 2 raised to 4 equal to 16 possibilities exactly once. Okay? So this is quite an elegant construction, very nice application of the directed Eulerian situation. Is that clear? So with this I'm done with chapter 1 in West book. Quickly move on to, what do we quickly move on to? We move on to chapter 2, and that is on trees. Okay, for what I want to do now, the graphs we'll be looking at will be simple graphs. So from this point on, they'll be simple and even undirected graphs. We don't want to look at directed graphs. Few definitions. Acyclic is called a forest. A connected without cycles is called a tree. We have already encountered examples of trees. Every path is a tree. Every path is a tree. Path with n vertices. That is a tree. Any other? It's what we call star. That is a tree. Connected graph with no cycles is a tree. Yeah, in fact, there is a characterization. You can quite easily prove this. What does this refer to? Maximum degree. This is the largest degree. In some sense, paths and stars exhibit the two opposite phenomena. Combinatorially, they exhibit two opposite phenomena in the world of trees. They are extremities in the world of in the set of all the trees. If your tree has at least 3 vertices, then you cannot just have a situation where each vertex has degree 1. That is just not possible. Because if a vertex has only degree 1, then you can only construct 2 vertices, not even third. Okay? So assuming that you have at least 3 vertices, there will be vertices of degree 3. So this is not expecting too much. But if there is no vertex whose degree is bigger than 2, then it must be a path. I'll leave this to you. Think about it and should be able to prove that. Another definition. Too happy with this chalk. A spanning tree is a subgraph, is a spanning subgraph which is also a tree. For example, that is connected. It's connected graph. It has spanning trees. Namely, that's a spanning tree. That's of course a spanning tree of that graph. That's not the only spanning tree of that graph. There are many others. Which others can I draw? From 1 I can go to 2, 2 I can go to 3, 3 I can go to 4. That's a different spanning tree from that spanning tree. Both of these are spanning trees of that graph. Okay? In this case, it should be easy to find out how many spanning trees that cycle has. Essentially, all I am doing is each time if you delete an edge, what you get is a spanning tree. This is true for any cycle. This is true for any cycle. You get the recipe for getting spanning trees. You just delete an edge from that cycle.
What is the spanning subgraph?
Okay, spanning subgraph is called spanning if it has every vertex on it. Okay. The definition of subgraph that we made doesn't have to have every subgraph, every vertex in it. Okay. Subgraph is too general a notion. Okay. Yeah, good you asked that. So spanning means you should have every vertex. So your subgraph should contain every vertex, and in its own right it should be a tree. Then you call it a spanning tree. In general, it will not be induced. Far from induced. Is that clear? So this idea of induced is, if your subgraph is spanning and also induced, then it will become the original graph itself. Is that clear? So induced in this setup is asking for too much. So we don't do that. We have already given this definition. Such a thing is what is called a leaf. A vertex degree of x is 1 is called a leaf. Or pendant vertex. It's called a pendant edge. For example, this graph has no leaf at all. Each vertex has degree, at least each vertex has degree 2, therefore it has no leaf. Whereas this graph, 3 and 5 are leaves. 4 and 5 are leaves here. All these are leaves here. The end vertices are leaves here. Okay. Every tree has to have at least one leaf. And in fact, if you are careful, it has to have at least 2 leaves. How does that follow? Because I try to construct a path whose length is as large as possible. Longest path. Then my claim is there cannot be any edge going out of y now. That is not possible. Where, if at all there is an edge going out of y, that will construct a longer path. If this is not the case, it will have to come back like that. In that case, you create a cycle which is forbidden because you are talking of a tree. Because you are talking of a tree, therefore, you are in a situation where you cannot really extend this further at all. In fact, the same thing is true at the other end. Absolutely the same thing is true at the left end also. So in fact, for the same reason y is a leaf, and for the same reason x will also become a leaf. So the conclusion is that every tree has a leaf. There are leaves in any tree, there must be leaves. In fact, most of the times quite many. Like in that case of star, the star graph has, except one vertex, all the other vertices, it has as many as n-1 leaves. In case of path, you have two leaves. So these, as I said, are extreme situations. You have only 2 leaves here. You have n-1, the largest possible number of leaves. So the actual number of leaves a tree has will fluctuate. It will actually fluctuate between 2 and n-1. Is that clear? I have used the fact here that tree by definition is finite. Okay. There are mathematical situations where you do talk of infinite trees. Okay, we are not talking of infinite trees. It is possible to define a tree as connected, no cycles, etc. on infinite number of vertices. For example, the easiest example of this is take the set of integers. Take the set of integers, set of all the integers z, in which you join the integer I to I plus 1. Join so age between I and I plus 1. 3 is joined to 4, 4 is joined to 5, and 3 is also joined to 2. So each vertex has degree 2 in that case. Each vertex actually has degree 2. So there is no leaf in that. Though it is a tree, it's an infinite tree. It has no leaves. There is no end vertex that you can see. This proof works because it's finite. You are in a finite situation. Otherwise that path may not end at all. So there is no such thing as longest path. In case of integers, there is nothing like longest path. Which path will you call longest? And you don't see the end of that path at all, etc. Okay, is that clear? So the conclusion for us, because we are looking at graph is finite object for us, tree is also finite object for us, is that every tree has a leaf. That gives us basic result. Proof? Okay. At least 2. Let n be equal to 2. What is tree on 2 vertices? Number of edges of t is equal to 1. So I would now make an induction on n. Let x be a leaf. So what is the situation here? Like x is adjacent to v and v may be adjacent to some other things there. If I now delete this vertex x along with that edge, what will happen is I'll get a tree on n minus 1 vertices. Deleting x and the edge xv from T, we get a tree T prime one vertex is less, one edge is also less. By induction, number of edges of T prime is number of vertices of T prime minus 1. Which implies that number of edges of T would be okay. So a tree with n vertices has n minus 1 edges. This procedure that you see there is elementary but quite useful procedure. We are going to use it repeatedly many times in the argument. What is it that I'm saying? In the tree I spot a leaf. I spot where the leaf is. There is at least one leaf in the tree. Delete that leaf along with the pendant edge. The resulting thing is a tree on n-1 vertices. That also must have a leaf. Then look at that, look at some leaf of that, delete the edge that joins and keep doing this. So sequentially one can go on shelving these leaves one after the other. One can go on throwing of leaves, essentially reducing to a situation where you will be left only with one edge. So this is something that we'll be doing quite successfully later on. It's a combinatorial procedure which is very useful. So this is sort of the beginning of that kind of thing. Spotting a leaf is important. You cannot really break, what I have done is, that happens to be an end edge, therefore it could be removed that way. I could not have removed, instead of that edge, I could not have removed that edge. That cannot be done. If I do that, the resulting thing would break. It would break into parts, and that is what, it's acyclic, has no cycles, but is not connected. Therefore it will have components. That's what we call forest. Okay? It's a union of trees is what we'll get. Whereas if you delete the thing at end, what you will get is a tree. Okay? Okay, so we have a theorem. Then the following are equivalent. Assertions are equivalent. One, yes, essentially T is connected and has no cycles. 2, T is connected and has n-1 edges. 3, T has no cycles and has n-1 edges. There exists a unique x to y path. This number 4 is really characterization of tree. Between any two vertices, I must have exactly one path on a tree. There is one path because the graph is connected, and there is only one because I have no cycles. This is the understanding. Okay, let's quickly see proof of this. Number 1 is just saying that it's a tree. Connected, no cycles means it's a tree. That's what we call a tree. So let one hold. Okay, if one holds, then T is a tree. Okay, that lemma there says that T has n-1 edges. Therefore 1 implies 2 and 3. Okay? Using lemma. Okay, so 1 implies 2 and 3. Let 2 hold. So now let's see what is given to me. I have a connected graph on n vertices and have n minus 1 edges. What prevents it from becoming a tree? What will make it a tree? It should not have cycles. Alright, so suppose it does have cycles. I mean, we are given that you have n minus 1 edges. Suppose this is basically the most elementary idea. From a cycle, if I delete an edge from a cycle, if I remove that edge from that cycle, and if your graph is connected, as such, it will continue to remain connected. It will continue to be connected even at the cost of deletion of that edge, because if you could go from one vertex to other, and if you have to use that edge, instead of using that edge, I could have gone around that way. Is that clear? I could just have gone around that way, because there are two ways of going from this vertex to this vertex. Okay? So there is a way of bypassing that edge. Because there is a cycle, there is a way of bypassing that edge. It's not essential. It is not really essential. Deleting still leaves us with a connected graph. This I have done at the cost of deleting one edge. I've deleted one edge, the graph still remains connected. Why is it still not a tree? Because it may even have further cycles. So this I may have to repeat sufficiently many times. So this is what should be called breaking cycles. You keep breaking cycles one after the other. There is no order in which you do that. But as soon as you spot a cycle, just delete one edge from that cycle. This will not disturb connectivity. Main thing is, if you started with a connected graph, it will still, the end graph that you will get will still remain connected. Continuing in this manner, we get a connected subgraph T star has no cycles. Is that clear? For example, if you just begin with a cycle, deleting one edge is sufficient. If you have the picture may not be, it could be like this. If I remove that edge, that resulting graph is still not, it still has cycles. But if I remove that edge and also that edge, then the resulting graph will have no cycles. Okay? Now T star is connected and has no cycles, therefore is a tree. So the lemma there says that if you have a tree on n vertices, you must have n minus 1 edges. But the pretension was that T star was constructed by removing edges. That means I did not remove any edge. Is that clear? That's a pretty proof of that. Obviously you could not have removed any edges. Since this is given to us, T star must be same as T. So no edges were removed. Which implies that T has no cycles. Okay. So 2 implies 1. Let 3 hold. Now I know that I have no cycles and have n minus 1 edges. Graph, acyclic graph. Acyclic graph, which is not a tree, each component is a tree. For a forest, each component is a tree. Graph that has no cycles, each component is a tree. Each Ti is a tree. Then the sum of Ni's is equal to n. How many edges does each Ti have? Ti has Ni minus 1 edges, the lemma. Using the lemma, E of Ti is Ni minus 1. So the total number of edges you get but I am already given that the number of edges is n minus 1. That implies that R is equal to 1. That means there is only one component. Only one component. And thus T is connected. So 1 holds. Alright, so 1, 2, 3 are equivalent to each other. Now let's assume 1 and prove 4. Just an idea. If your graph is already connected, so there is an xy path clearly. T is connected is given to you. So let 1 hold. I want to prove that 4 holds. Between x to y there is a path. If there are 2 paths between x and y, then I get a closed walk. Closed walk implies that there is a cycle, which is contradiction because one says that there is no cycle. So that is the proof that 1 implies 4. What about 4 implies 1? Between any 2 vertices, there is a path from x to y, therefore the graph is connected. That's the definition of connectedness. So clearly the graph is connected. If it did have a cycle, hypothetically, suppose there was a cycle, then I get two paths. I get one path going that way and one path going that way, which is a contradiction. From x to y, there will be one path, which is a contradiction to what is given. Therefore, I cannot have cycles. So that says that 1 and 4 are equivalent. Okay, this idea of breaking cycles is what we need to look at. This is a metroidal property. I'll elaborate on this in the next hour slightly more. So this connects with the things in linear algebra. Linear dependence and independence in vector spaces. The right abstraction of the graph theory setup as well as linear algebra setup is the study of what are called metroids.